As we've already established, a device, apparatus, or phenomenon that converts heat energy into mechanical work is a heat engine, and the efficiency of a heat engine is measured in amount of work performed divided by quantity of heat input. The second law of thermodynamics limits the efficiency of a heat engine and allows us to ascertain that no heat engine can ever be 100% efficient. So let's review what heat engines are and the types of thermodynamic cycles upon which they rely. In common, all heat engines use thermodynamic cycles that eventually return the state of a system to its more or less original state. We learned previously that a reversible process is associated with the largest quantity of work, and therefore, in general, reversible processes represent the most efficient processes that we could imagine. In a generalized heat engine, heat is extracted from a hot reservoir by the engine itself, which converts some of that thermal energy into mechanical work that is performed on the surroundings. The remaining heat energy that is not converted into work is deposited in a cold reservoir, and this process allows the engine system to return itself to its original state. Over the entirety of this cycle, the work that is performed is the negative sum of the quantities of heat energy coming from the hot reservoir and being deposited to the cold reservoir, respectively. And because our system returns to its original state, the overall change in internal energy for that system, the final energy minus the initial energy, is zero, because we have the same initial and final states. Therefore, any work that is done across this cycle by definition must be equal to a negative quantity of heat flow associated with the system. The second law of thermodynamics in all of its various forms and facets can be applied to thinking about heat engines and the processes that they undergo. In particular, the Kelvin-Planck statement of the second law is that it's impossible for us to either envision or create a system that solely converts heat energy exclusively into an equivalent amount of work without wasting any of that incoming heat energy. This statement of the second law establishes that heat engines are possible to create and use as real things, but that it is impossible to envision a heat engine that would take in heat from some hot reservoir, turn all of that heat energy into useful work, and waste or deposit no heat whatsoever to a cold reservoir. The most efficient possible engine is one that is entirely hypothetical. This most efficient hypothetical engine operates on a special thermodynamic cycle between a hot and cold extreme known as the Carnot cycle. The Carnot cycle consists of 4 individual steps. The first step is to take a system of an ideal gas located here on this pressure volume diagram at the initial state A and subject it to isothermal expansion at a hot temperature. Following this, from point B, we will remove our system from exposure to heat source and allow for residual heat energy to facilitate adiabatic expansion from points B to C on this diagram. Then, from point C in step 3, we will expose our system to a cold reservoir and allow for heat energy to flow out of our system. This isothermal compression brings us to state D on the graph. The final step in the Carnot cycle reverts us back to our original starting state A by allowing for adiabatic compression of our gas. During the isothermal expansion and compression stages of the Carnot cycle, temperatures are held constant. An ideal gas expands and compresses along an isotherm with constant temperature, which indicates to us that the average kinetic energy of the gas is unchanging. And if there's no change in average kinetic energy, and ideal gases don't exert any potential effects on each other, then consequently there's also no change in internal energy for that ideal gas system. And according to the first law of thermodynamics, any heat flow into the system is equal to work done by the system. The work that's done by a system during an isothermal process can be determined if we integrate this PDV expression, and we'll use an expression in turn for pressure that comes from the ideal gas law. Rearranging the ideal gas law to solve for P gives us nRT over V. Notice that everything in the numerator, N and R and T, are constants, so we can pull them out of the integral, and then just integrate dV over V, which integrates as the natural log of V final over V initial. During the adiabatic expansion and compression events of the Carnot cycle, maybe ones that are accomplished by removing our system of ideal gases and placing them in some insulating jacket, for instance, there may well be a temperature change, but no heat flows into or out of our system. By the first law of thermodynamics, then, any change in internal energy is exclusively due to work performed by the gases in our system themselves. We've also established previously that changes in internal energy for 1 mole of an ideal gas can be expressed as a constant volume heat capacity multiplied by a change in temperature. Therefore, the work that is performed by our gas during an adiabatic event is that gas's constant volume heat capacity multiplied by the difference in temperature it undergoes. So that if we put all of this together for the entire 4-stage Carnot cycle, we can express the work that is performed from step to step across each of the stages in the cycle. For example, to get from state A to state B, where we've performed some isothermal expansion, our gas needs to perform this quantity of work, which is guaranteed to result in a negative value for work performed, because by the end of stage 1 of the Carnot cycle, we'll have expanded to a larger volume than we started from. Following this, adiabatic expansion can be expressed in terms of the work performed based on the molar constant volume heat capacity of our system. We end up at a colder temperature than we started at, and consequently, our work performed is again negative. As we undergo isothermal compression, we have a smaller final volume than we did initial volume. The natural log of this quantity will therefore be negative, and that will cancel with the negative sign out in front, meaning that, all told, the work will be positive in stage 3, and also work will be positive in stage 4, the adiabatic compression, because we'll end up back at our high temperature, which is hotter than our cold temperature. And if we combine all of those relationships from the previous slide, we can re-express the efficiency of a Carnot engine not in terms of work performed per cycle divided by heat flow in, but rather in terms of the temperature of the hot reservoir and the temperature of the cold reservoir alone. As we do this, notice that we can express the efficiency of an engine as 1 minus the ratio of the cold temperature to the hot temperature exclusively in Kelvin. If we consider the implications of this relationship, those are that the efficiency of the Carnot engine can only approach 100% efficiency, or a decimal value of 1, in one of two limits. Either a limit as the hot temperature approaches infinity of that entire quantity, 1 minus Tc over Th, will provide us with a value of 1, because this denominator would cause this entire term to go to 0. Alternatively, in the limit as the cold temperature approaches 0, we also approach an efficiency of 1. In order for a cold temperature to approach 0 Kelvin, we would need to be able to create a system that was at 0 Kelvin. And we would need to keep that system at 0 Kelvin even all the while as we are depositing more and more heat energy from some hot reservoir into it. How would we get the heat to leave our cold reservoir and maintain a constant 0 temperature? We would need to send that heat to somewhere even colder. But because there is no colder temperature than absolute 0, there would be no way for us to physically offload that excess heat energy. Hence, we can never maintain a constant absolute 0 temperature, and so this limit is unrealistic. It's not achievable. Also, we cannot create an infinitely hot reservoir, so this limit is also unachievable, and as a consequence, even a Carnot engine, the most efficient engine we could possibly envision, never achieves 100% efficiency. We do know that the stages of the Carnot cycle are reversible, and what this means for us is that any heat that's associated with expansion, that's due to the high temperature side of our Carnot engine, must be equivalent to the heat that leaves our system during compressions that's associated with the cold temperature side of our engine. Or just slightly rearranging that relationship, we come to this line, which could be consolidated into one single argument, that the heat that's associated with the cycle as an entire whole at a particular temperature is equal to 0. This ratio, the quantity that represents a chunk of heat that's associated with a particular temperature, was regarded in the 1860s by the German physicist Rudolf Clausius as a very important measure of energy transformation. He would coin a term to describe this ratio that he borrowed from the Greek word for transformation, that term being entropy. Clausius was the first to coin the term entropy, but Sadi Carnot was the first to recognize the efficiency of a hypothetical idealized engine. Carnot's cycle implies that the difference between the hot side and cold side divided by the hot side temperature of a heat engine must be equal to the heat flow during the isothermal expansion plus heat flow during the isothermal compression divided by the heat flow during the isothermal expansion event. Or rearranging all of this relationship, we come up once more with the statement that we developed on the previous slide. This implies the importance of this quantity, a quantity or chunk of heat, divided by a particular temperature. If we think about tiny little increments of heat flow at a particular temperature, we in so doing define increments in entropy, ds. And so we'll make an equivalency between a tiny little increment in entropy, that energy of transformation under Clausius's definition, as a tiny chunk of reversible heat flowing into a system at a particular temperature. This allows us to integrate both sides of this expression and express entropy changes, delta S, in terms of a cyclic integral. The circle sign in this integral indicates integration across an entire cycle. It might be easier for us to simply drop that circle on the integral sign and define changes in enthalpy as an integral of reversible heat flow increments at particular temperatures. But like other thermodynamic quantities, such as internal energy, entropy too is a state function, which means that this general definition for entropy changes is also true for an irreversible process, granted that that irreversible process shares the same initial and final states as a complementary reversible process does. In this way, then, we can define entropy changes for certain thermodynamic processes in much the same way that we've defined work and heat for those processes. Under an adiabatic process, there is no heat flow into or out of a system, and so the numerator in our integral is equal to 0, and consequently too then is our change in entropy equal to 0. Thus, an adiabatic process is also known as an isentropic process for same entropy. Similarly, in a cyclic process, we integrate over a cycle and we get just as much heat flow in as we get heat flow out during a reversible cycle, so that the net quantity of heat is equal to 0, and the overall entropy change from the initial to the final state is 0. During an isothermal thermodynamic process, temperature is constant, so we could pull temperature out of our integral altogether. And that means that we're just integrating dq, which integrates as just that, q. For an isothermal process, then, we find a change in entropy is just heat flow divided by temperature. For an ideal gas, remember that an isothermal process is associated with no change in internal energy and work being equal to the negative quantity of heat flow into a system. We've already established that the work performed during an isothermal event goes as negative nRT times the natural log of the ratio of volumes. That means that the heat flow that's associated with that same isothermal process is negative of all of this. Negative of a negative sign is a positive sign. Divide that quantity by T, and we're left with nR times the natural log of ratios of volumes. During an isochoric process, volume remains constant, and we can express a quantity of heat flow under said conditions based on a constant volume heat capacity. Both number of moles and a constant volume heat capacity are constant quantities, presumably, and that means that we will integrate dt over T alone, which integrates as the natural log of the ratio of final temperature to initial temperature. And finally, for an isobaric process, where pressure is constant, we can express increments of heat flow in terms of a constant pressure heat capacity instead. And presuming that that constant pressure heat capacity is constant with temperature, we can pull it out of our integral and integrate dt over T once more. However, we can also relate the constant pressure and constant volume heat capacity through the ideal gas constant R, and we can take advantage of Charles' law to rewrite this expression for the entropy change associated with an isobaric process in terms of not the constant pressure heat capacity, but rather both the constant volume heat capacity and the ideal gas constant. In fact, this most recent expression that we've derived, that the entropy change is equal to number of moles times ideal gas constant times the natural log of ratios of volumes plus these terms in terms of constant volume heat capacity and temperature, is a general expression for the entropy change of an ideal gas, so long as we know how that gas's volume and temperature have been changed. We've talked about other things that aren't necessarily thermodynamic processes but involve heat flow. For example, we've described phase changes. During a phase change, like the melting of a solid or the evaporation of a liquid, a quantity of heat flows into our system commensurate with that heat energy required to fully melt or vaporize that system's contents. And all the while that this heat flow is occurring, temperature remains effectively constant. Because most phase changes occur in exposure to constant pressure environments, we could also write down the heat flow that's associated with a phase change in terms of an enthalpy change. And so, in this way, we can define a change in entropy that's associated with a phase change in terms of a number of moles, and enthalpy associated with the phase change itself, and the temperature at which that change occurs. However, when we try to describe entropy on a microscopic scale, the description of what entropy truly represents becomes a bit muddled. The easiest way for us to describe what entropy represents at the microscopic level is to think about analogies to macroscopic systems. When we're dealing with large-scale quantities of particles, like the number of particles that would make up a macroscopic quantity of ideal gas, for instance, we can describe those particles collectively as an entire system whole, rather than on a discrete particle-by-particle basis. We use quantities like pressure, volume, and temperature to describe the macroscopic state of our system of particles, and in so doing, have described that system's macro state. However, we keep in mind that each individual contributing particle in our entire system has its own individual set of properties. And, given those properties, we could think about the system on an individual particle basis. In so doing, we're considering microstates for that system. To give us an analogy, let's think about tossing 4 fair coins. There are 1, 2, 3, 4, 5 different outcomes that could be envisioned if we were to toss 4 coins one after another. Either they all come up heads, they all come up tails, 2 of them are heads and 2 of them are tails, 3 of them are heads, 1 is tails, or 3 are tails and 1 is heads. But, given each of these 5 outcomes, there might be multiple ways in which we could achieve those outcomes. The number of ways that we could achieve an outcome is representative of a microstate that corresponds to a larger scale macroscopic state. So let's put some math to this. Suppose that we do toss 4 separate fair coins. We could get one of 5 results representative of macrostates for that system. But there might be numerous ways for us to achieve any one of these given macro states. So, we might ask, how many of these ways are there? The number of ways in which we could achieve one macroscopic outcome is measured by the number of microstates that correspond to that outcome. The number of microstates, in turn, we can calculate from a probability distribution. The number of coins that we've got, represented here by capital N, factorial, divided by the number of heads we see when we toss those coins, factorial, multiplied by the difference between the number of coins and the number of heads, quantity factorial. Keep in mind that when we take factorial quantities, 0 factorial is defined to be 1. To calculate the number of microstates that are associated, for instance, with 2 heads and 2 tails, we can use that microstate formula at the right to divide the factorial of the number of coins that we've got, which is 4, by the number of heads we would see, which is 2 factorial, multiplied by the difference between the number of coins and the number of heads, quantity factorial. This calculation is equivalent to 4 times 3 in the numerator divided by 2 in the denominator, and it gives us the number 6. In fact, if we repeat this calculation for all of the other macrostates we've got, we'd find that the number of microstates that correspond to all of our coins landing heads encompasses just one possible way to make that happen, which makes physical sense. If we toss one coin after another, then there is only one set of circumstances that leads to all of them showing heads. That the first one we toss is heads up, the next one we toss is heads up, the third one we toss is heads up, and the final one we toss is heads up. There is no other way for that outcome to be achieved. When we apply our microstate calculation to either 3 heads and 1 tails, or 1 heads and 3 tails, we get in either case 4 ways to make that happen. There are 6 ways to make 2 tails and 2 heads show up, and there's only one way to make all of our coins land tails. The real idea behind thermodynamics, and especially the concept of entropy, is that thermodynamics deals with things that are most statistically likely to happen. If we toss 4 fair coins, the most statistically likely thing that we'll see as a consequence of tossing those coins is that 2 are heads up and 2 are tails up. The reason that we are most likely to see that is that there are the most number of configurations or microstates that lead to that macroscopic outcome. Ludwig Boltzmann recognized the connection between this concept of microstates and entropy, and in particular is famed for this entropy relation, which is inscribed on his tombstone. S, a measure of a system's entropy, is equal to the Boltzmann constant, K sub b, multiplied by the natural log of the number of microstates, indicated here with the symbol capital W. Let us use Boltzmann's equation, then, to compute the entropy that would be associated with all 4 of our coins coming up heads, and separately, the entropy that would be associated with 2 heads and 2 tails. The entropy of 4 heads showing up when we toss 4 fair coins is given by Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin, multiplied by the natural log of the number of microstates that are associated with that macrostate. Previously, we found that there is only one way or one microstate that generates the macrostate of 4 heads. So we take the natural log of 1, and the natural log of 1 is 0. So our entropy is 0. The entropy associated with 2 heads and 2 tails, though, is still Boltzmann's constant, but this time multiplied by the natural log of a non-1 quantity. We found that there were 6 microstates that gave rise to the macrostate of 2 heads and 2 tails. So the entropy associated with this macrostate is 2.5 times 10 to the minus 23 joules per Kelvin. That might seem like a small number, but let's compare it to the entropy of the other outcomes. The entropy of rolling 4 tails is 0 for the same reason that the entropy of finding 4 heads was 0. The entropy of getting 3 heads and 1 tail or 3 tails and 1 head are equivalent to each other. There were 4 microstates which led to that macrostate outcome, and the entropy here is 1.9 times 10 to the minus 23. Notice that the highest entropy is associated with the most likely or most probable outcome that our system could attain. This is not to say that it's impossible to get 4 heads or 4 tails. It's just that statistically, we are much more likely to find two heads and two tails than any of these other configurations, owing to the entropy that's associated with that macro state. In thermodynamic systems comprising atoms and molecules, note that we don't have just 4 particles, but on the order of Avogadro's number worth of particles. That means that there is an almost impossible to fathom number of different possible microstates that could be associated with the various possible physical constraints and characteristics of each individual particle that makes up our system. It is far more easy for us to describe the macrostate system than it is to describe each and every microstate. So, we will try to use the entropy associated with the macrostate of a system to deduce something about the nature of its microscopic makeup. As an aside here, I'd like to share with you a thought experiment that James Clerk Maxwell, the Scottish physicist of Maxwell equation fame that govern electromagnetism. In this Gedanken experiment, a pure thought experiment, Maxwell envisioned, in a letter that he wrote in 1867, 2 chambers separated by a wall that has a movable frame which can selectively be opened or closed in order to allow select gas particles to be exchanged between one chamber and a next. Maxwell envisioned some sort of creature that would sit outside of these chambers and selectively open this door to allow only certain particles to pass through. In particular, this creature that the Lord Baron Kelvin would later dub Maxwell's demon would only allow slow-moving molecules to pass through this entryway. The consequence of this would be that one side of our chamber consists of particles that are only ever becoming hotter, while the other side of our chamber only consists of particles that are ever only growing colder over time. This would be in direct violation of the second law of thermodynamics as it was postulated in the mid-1800s. But critics point out that Maxwell's demon, this creature itself, would have to perform work on this system in order to selectively allow only slow-moving particles to move into the cold region and retain fast-moving particles in the hot one. And it would be this sort of work performed by that external agent that would render the entire scenario in compliance with the second law of thermodynamics. To facilitate this seeming violation of the second law, work has to be performed on the system. Outside of this thought experiment, the second law of thermodynamics seems to be a universal truth. So, let us think about trying to tie this concept of energy to microstates for a system that comprises many more than just 4 coins and is made up of real chemical particles. Suppose that we have a system of helium atoms that are exposed to a temperature of 0.2 Kelvin. Eventually, we will learn to calculate how many individual helium atoms in a sample of helium occupy each of these distinct energy levels, and we'll learn how to compute what those energy levels are in the first place when we explore statistical mechanics later on this semester. We'll also be able, at that point, to predict what the change in distribution of these helium atoms will be if we increase the temperature to a whopping 0.3 Kelvin from 0.2 Kelvin. What will happen in that case is that our energy levels will stay virtually the same, but with the increase in temperature, each individual helium particle gains on average a little bit more kinetic energy, which facilitates occupancy of higher and higher energy levels the higher the temperature grows. One way that we can think about this excess thermal energy in the form of increasing temperature is that the increase in temperature facilitated the distribution of particles across a broader swath. The energy that was put into the system helps that system spread out in terms of energy. But this also has the consequential effect of rendering that thermal energy unavailable for any further expenditure. This is energy that will be contained within the system itself due to microscopic machinations. But it will not be energy that is ever available to do useful work for us. Thus, a quantity of energy that's input into a system goes towards spreading out the energy of the system overall. This is the entropy that's associated with the system. And once devoted towards this spreading out, that incoming energy can no longer facilitate mechanical work expenditure. Thus, we can never envision a system that does work with 100% efficiency. Earlier, we recounted the Planck-Kelvin statement of the second law of thermodynamics. But a more fundamental way to state the second law is to state it in terms of entropy changes. And in particular, we can classify entropy changes under the guise of the second law in accordance with whether processes are reversible or irreversible. For an irreversible process occurring in an isolated system, the direction of spontaneous change will be associated with changes in entropy that are positive values or greater than 0. And a non-spontaneous process will be associated with a change in entropy that's less than 0 for the entire isolated system as a whole. In comparison, for a reversible process, an entropy change is equal to 0. This is because, effectively, during a reversible process, there is no direction of spontaneity, since the system that we're using comes into quasi-static equilibrium at each step along its progress to some final state. Consolidating all of these statements down, we can define entropy as the so-called arrow of time, and we interpret entropy as implying that the total disorder of an isolated system should be expected to naturally increase over time. To illustrate this, let's use a specific example where we envision a rod consisting of metals at 2 different temperatures held in contact with each other. And let's imagine that heat flows from one of them to a second. We'll say that the rod that's shaded in red is at temperature T1, and the other rod shaded in yellow is at temperature T2. Heat flows from red rod to yellow rod, and the entropy change that's experienced for the system as a whole, this collection of 2 rods touching each other, is given by the heat flow associated with rod 1 at rod 1's temperature, plus the heat flow that's associated with rod 2 at rod 2's temperature. The same quantity of heat flows out of rod 1 and into rod 2, though, so we could factor out an absolute value of this quantity of heat, Q sub P, and use a negative sign in association with rod 1's temperature to indicate that heat is exiting rod 1, a positive sign in association with rod 2's temperature to indicate that heat is entering rod 2. And what's more, if heat is going to flow spontaneously from rod 1 to rod 2, then by definition, the change in entropy that we experience in so doing has got to be greater than 0. What must be true in order for this expression to be greater than 0? Well, one of two things. Either that there is 0 heat flow altogether, which we will presume does not happen, or that negative 1 over T1 plus 1 over T2 is greater than 0. If that is the case, then I could rearrange this expression and show that 1 over T2 must be greater than 1 over T1. And if I do this, then I can take the reciprocal of both sides. However, when I take a reciprocal of fractions, I also must flip an inequality sign around. So if I take the reciprocal of both sides, I have to flip the inequality from a greater than sign to a less than sign. And the only way for this entropy change to be greater than 0, and therefore represent a spontaneous process, is to have the temperature of rod 2 be less than the temperature of rod 1. We already established through the 0th law of thermodynamics that heat naturally flows from hotter things to colder things. If the temperature of rod 1 is higher than the temperature of rod 2, then rod 1 is hotter than rod 2, and we would have expected from the 0th law that heat would flow naturally from one to the other. The 2nd law of thermodynamics is what facilitates the 0th law of thermodynamics. And we conclude that for heat to be able to flow spontaneously from rod 1 to rod 2, the temperature of rod 2 must be smaller than the temperature of rod 1, something that was already intrinsically obvious to us. This is why we see spontaneous heat flow from hotter to colder systems. Similarly, we can explain the tendency for a gas like an ideal gas to expand naturally into a vacuum, increasing its volume, but not changing its temperature, in accordance with the 2nd law of thermodynamics fundamental statement. One way that we can express the generic entropy change for an ideal gas is if we know something about the ratio of volumes and temperatures from initial to final states. However, if temperature doesn't change, then the natural log of the ratio of temperatures goes to 0 because we take the natural log of 1 again. And we can describe the entropy change for an isothermal process that involves the expansion of an ideal gas in terms of a ratio of volumes. And if a final volume, in particular, is larger than an initial volume for our ideal gas, then the natural log of that entire ratio of volumes is a positive number, and therefore the entire right-hand side of this equation is a positive number. And delta S is consequently larger than 0. Thus, it is spontaneous for an ideal gas to expand against a vacuum and increase its volume. Reversible processes have an entropy change across the entirety of a cycle that's equal to 0 because all of the entropy changes associated with our system and that system's surroundings are balanced. There is no natural tendency for this system to go forward or backward, as forward and backward sort of lose all meaning, since the system is virtually always in equilibrium with its surroundings. We use the term quasi-static to imply this set of conditions. From here, we have the groundwork to build a more comprehensive understanding of entropy and relate it in turn to the work that's associated with thermodynamic systems. And that is what we will do beginning in our next lecture.